There are a couple of other things we can do with quartiles, percentiles, that help us in our visual ideas. But once we've established which kind of quartile we want to use, the inclusive or the exclusive, we can then do stuff based on that. So let's go back to our JD Power data. Now notice in this very beginning setup, they did give me quartiles. Right up there, summary statistics. I've got the mean, the standard deviation, the count. And I've also got 3 quartiles. And if I ask what command did they use, it just says quartile. They didn't used to differentiate. So how the hell do I know which one it is? So let's cheat. And over here, we'll do the quartiles both ways. So I'm going to write the quartile equals. You see how it shows that third line down there? I've got exclusive and inclusive, and then at the bottom it just says quartile. That's the old version. So I don't know which one it is. So I'm going to do both of these. Quartile.exe. What's the data? Well, the data is over here, my defects data. And then I need to tell it which one do I want. And it says I put a 1, a 2, or a 3 there. First quartile, median, or third quartile. I'm just going to put 1. If this is the same, then they're doing the exclusive ones. Clearly, it isn't. So I'm going to write at the top of this, I'm going to write exclusive in this column and inclusive in this column. Again, highlighting the same data. 1. The hell? Oh, I made a copy error. Let's fix that. There. So the compatibility, the old version is the inclusive quartile. And the exclusive would be, that's why they put the differentiation in. So if you just type quartile, by default, it does inclusive. And I can do 1 and 2 and 3. But based on what we were looking at, just knowing the quartiles, just knowing the median, and the quartiles, I've got more data outside quartile 1, lower than Q1. I've got more data above Q3. So I think it would be to my benefit to have 2 more pieces of information. What are the extremes? So instead of just doing quartiles, I like to generate what's called a 5-number summary. And the 5-number summary includes all 3 quartiles. But it also includes the max and the min. So this gives me the entire data set contained within these 2 values, and then where my quarters are and where my middle is. If I were to put these on a number line in order, let's actually check our numbers again from the data set we were just looking at. I have 165, 185, and 204. What's the minimum of this data? I know we did that before. Does anybody remember? Well, let's check. Minimum of all of this is 139, and the maximum of is 265. So on my data, I need all 3 of these numbers. So I'm going to write them down. 139, 165, 185, 204, 269. Oh, 265. I can copy correctly. So I know these two numbers go on the ends. But if I want to scale this correctly, these numbers are all closer to the left than they are to the right, aren't they? 139 to 165 is only about 30. Then this is only 20 higher. This is only 20 higher than that. And this is a ways over, right? So if I want to do these to scale, I get a picture that looks more like this, don't I? These get used so often that we tend to put that interquartile range as a box with the high and the low just as strings going out. I hope to no one's surprise, this is called a box and whisker plot. I know where the center is. There's my median right in the middle of the box. Usually, if it's not symmetric Q1 to Q3, then maybe the median's not right in the middle of that box. But I can clearly see that this data is skewed. Which way is it skewed?
Maybe probably maybe right skewed because it has a tear on the right going out that way.
Tail on the right.
No, the weight to the left.
Weight on the left. Page 127. I see several different types of data. Mostly symmetric, clearly skewed left, clearly skewed right. Almost uniform. Almost straight across. And the corresponding box and whisker plots that go with them. You can do box and whisker plots in Excel. Yes.
How would you tell the difference between uniform and
that normal idea?
I do.
Okay, let's take a closer look at those two. And I can see there's much more of the same size in all the quarters, aren't there? Whereas here I've got a big jump between the low and quartile 1 and between quartile 3 and the max. So the normal has these longer tails on each side and the uniform doesn't. If we're measuring this more precisely, there's actually a number we can calculate that will allow me to differentiate between these two that has to do with how thick or thin the tails are. It's called kurtosis. The larger kurtosis values tell me that I have bigger, thicker tails. So this, there's no real tail on each side. So these tails are really big, they're thick. And these tails are kind of thin. So this would have a larger kurtosis than this. That is the only time I will talk about kurtosis in this class. It is really more commonly used in physics terms than it is in statistics terms because it's related to a third moment related to wobble in rotating bodies. Bizarre connection. But what I don't see here, what if this tail actually had a gap in it? Or this tail had a gap in it? Outliers. There's no indication here about outliers, are there? So quite often, we will create a new value and we'll measure this distance, right? That's our interquartile range. In this case, 204 minus 165 is 39. When we were dealing with standard deviation, we had the idea that if you were 3 down or 3 up, that was really unlikely. So we called stuff that had a z-score bigger than 3 or smaller than -3, We call those outliers. Here, I want to use our interquartile range. And I am going to define fences. We have a low fence, and we have a high fence. The low fence is Q1 minus 1.5 times that interquartile range. And the high fence is Q3 plus 1.5 times the interquartile range. So really, I'm saying if you take this whole box, stretch it by half, and move it down here, anything that's outside of that is an outlier. Anything that's outside of that up here is an outlier. In our data, what are these fences?
Maybe like high.
Oh, well, let's figure out what they are. Let's figure out numbers. Calculate for me.
165 is Q1,
Yes,
and it's minus 1.5 times 39. That's like
that is exactly it, Leo. So hang on and let everybody else do these calculations along with you. Let's get there. Now here it's going to make a difference which quartile we used, right? If I use the inclusive versus the exclusive. So I need to know which quartile I'm using, and I need to be consistent in my usage. So since we used the inclusive ones, I need to make a note of that somewhere. Ideally, to whomever I am presenting this information to, if they care. Because the difference between inclusive and exclusive is very small. In our case, it was a point. So it's not going to typically be a very large issue unless there are more uniform pieces of data with some stretch to them. So in our case, 165 minus 1.5 times 39, and then 204 plus 1.5 times 39. Do we have outliers in our data? Oh, thank you. Good catch. That's going to make a difference. Okay. Based on those, do I have outliers?
Yeah.
Why?
262. Then when you were explaining it, you said you take like half the box or quarter of the box, you can go left past Q1 and you can go right past Q3.
Mm-hmm.
It's past that area, then it's out there.
Exactly. And I know that on our picture, I've got a 265 up there, right?
Yeah.
So that means that this first high fence is going to be here. On the other hand, the low fence is way down here. So I do have, and this kind of matches my idea of the skew, right? I've got an outlier to the right. It should be skewed right. On the top of page 128, we will see exactly that same setup. If you do the inclusive quartiles, you get these values that are in the book. But if you do the exclusive quartiles, you get different values. So it's going to depend on what you do with your quartiles. If you do this in Excel, it does it by default vertically. There's my box plot. The interquartile range is in blue in that center piece. You'll notice there's something else. It's a little faint, it's kind of hard to see. In the middle of that blue region, there's an X.
The hell is that?
That's the average. All of this is based on mean and not mean, but median, and quartiles have nothing to do with mean, but they put the mean in the box plot automatically. Why does this help me? Or why would I find this useful? Mean is sensitive to outliers, right? So if the mean is bigger than the median, if it's above that second line, I should be skewed in that direction. If it's below, I should be skewed low. If they're right on top of each other, I should be roughly symmetric. So that's another indication helping me remember what direction we're skewed. You'll notice in this piece, I've also done our mid-hinge. The hell's our mid-hinge? And it was another measure of center.
It would be the Q1 plus Q3 divided by 2.
The average of the two and the two quartiles. Great. That is fairly close to the median, isn't it? 185, 185.5, 184.5. Again, whether I'm doing inclusive or exclusive, they only differ by very little. This tells me that that interquartile range is fairly symmetric. If that was stretched in one way or another, I'd be able to compare the mid-hinge to the median. More questions? Under insert charts, box and whisker is a defined option next to our histograms. I did also put percentiles in here. You'll notice some of the percentiles are giving me errors. Because again, percentile has an exclusive and an inclusive version. This pisses me off. Come on, make up your mind, pick one. I kept saying we had to go up to the next value, right? If I ask for the 100th percentile, there is no next value, is there? That's why this returns an error when you ask for the exclusive 100th percentile. You have to go up to the next number, and there isn't one. If you do the inclusive, it'll give you the top number, or at least it'll give you the spot where the top number is. There are 33 numbers in my list. It's the 33rd spot. I don't use percentiles anywhere near as much as I use quartiles and deciles. But I don't know what sort of statistics you will be looking for in your business curriculum, in your career. Questions? Okay. When we were looking at variance calculations in Excel, there was another thing that popped up. Covariance. One of the things that is often useful to me is to examine whether or not two ideas are connected. Wait a minute, I've seen pictures where I was talking about connection between variables. What did we do with data where we were trying to do connections between them? We made pictures. What kind of pictures did we make? I promise you all did this. It was on the homework I gave back, so I know you did it. With our pharmacy issues, right? Zolona and Zalparm, I did two drug manufacturers. There was a homework question about that. We made a scatter plot, right? Covariance is related to our idea of scatter plot. Now, there is a formula for covariance that I have literally never used. When my covariance, which by the way, what was variance? Variance was like sigma or S. If I've got two different pieces, let's say our variables are X and Y, then I can talk about the covariance between them. We'll sometimes use sigma XY for this setup. And while I appreciate that, I can tell you with some certainty that the thing that bothers me about this is the way we actually do this calculation. When we did variance, that was our standard deviation crap, right? So I took the deviation for each one. I squared them, added them all up, and I divided by how many there were, or by one less than that. Then I took square root to get the standard deviation. I've got two variables. I don't need to square, I can multiply them by each other. That's why there's an X and a Y down there. This formula absolutely sucks. Don't bother. I just want you to see what I'm writing down. You add up the product of all of the variations between them. But that means the units for this are X times Y. So we were doing drug sales in that pharmacy question, right? So it would be dollars for Delona times dollars for Z. This is again, the units stink here. I don't like the units. But what I can actually make as a statement for this is if the covariance is positive, then these are varying in the same direction. When one goes up, the other goes up. When one goes down, the other goes down. If my covariance is negative, then they should vary in opposite directions. When X goes up, Y is going to go down. When Y goes up, X is going to go down. If the covariance is zero, or really, really close to zero, then they're basically unrelated. Now, if I think about housing prices, is the following pair of ideas for houses related? The price of the house and the number of square feet in the house. Are those related? What do you think?
Yes, they would be, they'd be directly proportional to each other.
So I would hope that there would be a positive covariance. Bigger houses should sell for more, smaller houses should sell for less. Ideal. If I actually sit down and create a set of data that has this information, square footage price in thousands of dollars. So 861 is $861,000 for that house. But that house is 3,570 square feet. That's huge. I can create a scatter plot from this. Insert scatter plot. There we go. Square footage, price. And I see they go the same way. If I actually ask for the covariance, I need to put an equal sign there, equals COV covariance. There are two versions. Why are there two versions? It's a dot P and a dot S. What's the difference between a dot P and a dot S? Bingo. If I think this is all the houses, I'll use the dot P. If I know this is just some of them, I'll use the dot S. Covariance dot S, first list, comma, second list. Positive number. It's a fairly big positive number. It's a variance, so it's squared, right? It'll be huge. But the units for this is dollars times square feet. That's useless. But if I really want to know, are those related? I gave you another way to do this. What did we do? Leo?
We like check the correlation.
Correlation. The correlation coefficient R. Pearson correlation, guy who did it. I get that right over here from the data. I right click on one of my dots and I add a trend line. And it automatically starts formatting that trend. Oh, go back to the trend line, dang it. It automatically starts formatting the trend line for me. And the two options down at the bottom there ask me for the ability to display the equation or to display the R value. Now it actually gives me R squared. So I'm going to click on that, and it's going to tell me that R squared is 0.6952. Somebody take the square root of that number.
It's like 0.8337.
Now it could be positive or it could be negative, right?
Yeah.
Because when I take a square root, I know I get two of them, but I know this one is positive because they go in the same direction. As square footage gets bigger, price is getting bigger. If I have data that goes the other way, I'll get a different correlation coefficient. Here, on page 133, is our crazy ugly formula for correlation coefficient, which I will never make you do. And several examples. Positive correlation, that's fairly strong. Negative correlation, that's fairly strong. A weaker positive correlation because they're more spread out around that trend line. A more weaker negative. The trend line is basically horizontal here. Basically horizontal, even though this is really tight. These are technically not correlated. I don't have a growth or a decrease connecting them. Question
It
there?
would be more like how much Y is dependent on X and how much they affect each other either directly or indirectly.
Yes, but we're only measuring a linear relationship here. Correlation is only after straight lines. So if they have a relationship that isn't straight line, let's say I was looking at flight speed of a bird based on its wing size. Believe it or not, flight speed of a bird is not a linear relationship. It's a quadratic relationship. If I plot that data, birds with really long wingspans don't fly as fast because they slow down as the wings get really big. A lot of these birds save their energy because they're so huge, they just glide. Look at an albatross. An albatross has wings that are 6 feet across. It's slow. It also flies all the way across the Pacific Ocean. So it is possible to have a nonlinear relationship in my data and still get a correlation coefficient out of Excel that doesn't actually reflect that nonlinear relationship. An interesting note on these pictures, all of the correlation coefficients are always between -1 and 1. Every time. If you've got a correlation coefficient that is exactly 1, your data is in a perfectly straight increasing line. If you've got a correlation of -1, your data is in a perfectly straight decreasing line. I don't know what the slope is, but it's a straight line. If it even spreads out from that line a little, then we come down from 1 or up for -1. But you're never going to get something smaller than -1 or bigger than 1. It turns out this is related to cosines in angles. And cosine is always between -1 and 1. If you want to know more about that, I talk about it in linear algebra. It's really cool. But it's definitely not here. More questions? So I've had single variable data, univariate. I've had bivariate data for my scatter plots. We can have multivariate data. We can do these same ideas in multivariate data. They're just harder to visualize. Because if I try and start looking at relationships between 3 pieces of data, I'm going to have to draw these pictures in 3D. And unless we all have those funny red and green glasses, we're not going to see them very well. If you put on a VR headset, you might be able to take your 3D and twist it around in your computer. But what happens when you have 4 or 5 or more variables? It doesn't become easy. There are ways to slice up your data and look at, oh, I've got 5 things that are related. Let's look at these 2 or these 2 or these 2. And then I can play with how they go together. You'll cover some of that in the discussion of multiple regressions in decision analytics next semester. We did histograms. And when we did our histograms, we threw data into bins, right? So if I want to do averages, means, medians, standard deviations for data that is grouped, then I have to take into account more information about the size of the group and the way we put things together. So let's suppose I had a bunch of different data. Hey. Yes, here it is. I look at my histogram, right? My frequency distribution. I no longer have the original data. I just have this frequency distribution. What's the mean of this data? How the hell am I supposed to know that? Hang on. There isn't enough information here right away. Let me copy this down. Oh, that's a 14 out of 19. So I have bin widths of 4, and I have a frequency for each bin. I know there are 7 values between 2 and 6. And if I'm looking at the histogram, I would put that bar on the histogram at height 7, width 4. Yes? Let's suppose for a moment that this is that rectangle on my histogram. I want you to balance this on your finger. Here are my x values across the bottom, from 2 to 6. What x value am I going to put my finger at? 4, because that's the middle. It's 7 tall. I'm going to put it at a height of 3.5, right? But I'm going to put it at an x value of 4 to balance this. That's the midpoint of each bin. So let's actually write that. Let's write the midpoint of each bin. So the midpoint of this one is 4. What's the midpoint of this one? Aha! I'm going to split all of these exactly in half. Right? And so here's my assumption. My assumption is that I can consider this entire rectangle be at the value 4, because that's the middle. I can consider the next rectangle to be at the value 8, because that's the middle. If I do that, then I can say what I really want is I want 7 4s and 12 8s and 3 12s. Hang on a second. This now helps me figure out what the average is, because I can add up all the data, right? I have 7 4s and 12 8s and 3 12s and 2 16s and 1 20. I can add up how many I've got. So I take the frequency times the midpoint, and I add those up. 7 times 4, 12 times 8, 3 times 12, 2 times 16, and 1 times 20. What is your total?
Like 215.
I hope it's not a 15, because all of those numbers are even.
212.
Aha. That's the total. That's my sum. How many values do I have?
5.
Hold that thought. No, I have way more than 5, Leo. I have 5 categories, right?
Yeah.
But each category appeared more than once. I have to add up the frequencies to find out how many total data values I have from. I have 25 of them. So my average estimated is 212 over 25. And I can do that. 8.48. A weighted assumption of an average. You know what else I could do? I could do the standard deviations the same way. Because I would say, oh, the value here is 4. I need to know how far away that is from the average, right? I take the variation to do the standard deviation estimated. I'm going to take value minus the average squared. Value minus the average. Value minus the average. I'm going to take all of those and I'm going to divide by, this is sample, right? So I'm going to divide by number of items minus 1. And then I'm going to take the square root. If I had the original data, I wouldn't have to do this bull crap because I'd be able to plug it into Excel and say, do the standard deviation, walk away. But I don't actually have the data. I only have the summary. I can still ask, how varying is this data? Once I get the standard deviation, I can get the coefficient of variation. It's not 100% accurate because it assumed that this value between 18 and 22 was actually 20. Maybe it was 18, maybe it was 19, maybe it was 21, maybe it was 22, I don't know. So this is an estimate, and it will be off when compared to the exact calculation. If I had smaller bins, I'd get a better estimate. If my bins were all size 1, I'd have the original data. So even when I don't have the exact data that was originally provided, I can still go through and create all of these numbers and measures the same way. I can do median and mean. I do median and quartiles here. I have 25 pieces of data, right? What spot is the median? There you go.
It'd be the 12 minus 8.48 squared.
This thing?
Yeah.
That's the variation on that bin. That is not the median. The median goes back to the original data. What position is the median in? Say again? The 13th spot. 25 data values, 12 on the low end, 12 on the high end. The 13th one is exactly in the middle. Let's do a cumulative frequency. I'm going to write up here. Cumulative frequency. There are 7 in here. There are 12 here. That's 19. 13. I passed 13 along the way, didn't I? I passed 13 along the way. So the 13th number is in this bin. And that means based on my assumption, the 13th number is an 8. The median of this data is roughly 8. That again lends me to things about skew, right? Because now the median is smaller than the mean. This data is skewed to the right. I get the same conclusions even without the exact numbers. By the way, if you really want to finish this out, there's the rest of our cumulative frequency. I am walking right past this section in the textbook. But if you really want to know more about skew and kurtosis, the actual calculation and formulas are here. And this is why I hate kurtosis, because that's disgusting. Skew is just as bad. The only thing I will tell you that actually makes me interested in these formulas in the slightest, the skew formula has a cube on it. Our standard deviation had a square on it, right? So this is measuring how far out we are even more. Kurtosis has a 4th power on it. And then they're subtracting this other number, and why? Why would you do that? There are lots of really interesting reasons. They should have been mentioned in DT 100. about excess kurtosis and the normal distribution. It's really a very niche statistic to calculate. Question. All of this so far, I gathered my data and now I want to tell you about it. I made pictures so you can see it easier. I create summary pieces of information to describe the data to you. So what? This tells me what already happened. How do I figure out what's going to happen? How can I be predictive rather than descriptive? To do that, I need a little bit more theory. And that means I need to talk about probability. And that is our next chapter. 2 pieces of information. 3 content-heavy chapters is plenty. This is exam 1. If you look at our schedule, originally that was going to be a week from today. It got moved. The exam is Monday the 23rd. The homework from chapter 4, which we have just finished, is due on Wednesday. Friday's class will be hybrid. I will be in the middle of the makeup for that Middle States math competition. I won't be here. I will pre-record it and distribute it to you like I did on the snow day. And then on Monday, I'll have the exam. That means that you'll be seeing stuff on this probability chapter that we're not really going to use on that exam. There is a review sheet on our Canvas page. The key to that review sheet will be posted after Wednesday's class. If you have questions, you should come hang out in my office hours between now and then. I will see you all on Monday. I hope you have a question, Chris.
When we have class one day, like, are we gonna start content for chapter?
Yes, we're going to start chapter 5 on Monday. I've got to keep going and I can't just leave them off out. I will see you then. Have a wonderful rest of your day.